Hello everyone, myself Shivangi Desai, your instructor for the video series of Data Mining and Business Intelligence. Today's our topic is Concept Description. So let's get started. Data Mining. Data mining is a process of analyzing large set of data from the data warehouse in order to find out the patterns or insight from it. Data mining can be classified into two categories. First, descriptive data mining, and second is predictive data mining. Descriptive data mining describes the data set in a concise and summative manner and presents interesting general properties of the data. It is used to describe main features of a collection of data in quantitative terms. Second is predictive data mining. Predictive data mining analyzes the data in order to construct one or a set of models and attempts to predict the behavior of new data sets. It combines database analysis with multivariate statistics and artificial intelligence. The simplest kind of descriptive data mining is called concept description. Next is data generalization. Data and objects in databases contain detailed information at the primitive concept level. It is useful to be able to summarize a large set of data and present it at a high conceptual level. Data generalization is a process that abstracts a large set of task-relevant data in a database from a low conceptual level to higher ones. Data generalization is a summarization of general features of objects in a target class and produces what is called characteristic rules. The data relevant to a user-specified class are normally retrieved by a database query and run through a summarization module to extract the essence of the data at different levels of abstraction. Well, data generalization has two methods. First is data cube approach, which is also known as OLAP approach. In the data cube approach to data generalization, the data for analysis are stored in a multi-dimensional database or data cube. In general, the data cube approach materializes data cubes by first identifying expensive computations required for frequently processed queries. These operations typically involve aggregate functions such as count, sum, average, and max. The computations are performed and the results are stored in data cubes. Such computations may be performed for various levels of data abstraction. These materialized views can then be used for decision support, knowledge discovery, and many other applications. Next approach is attribute-oriented induction. The essential operation of attribute-oriented induction is data generalization, which can be performed in either of two ways on the initial working relation, that is attribute removal and attribute generalization. If there is a large set of distinct values for an attribute of the initial working relation, but either there is no generalization operator on the attribute or its higher level concepts are expressed in terms of other attributes, then the attribute should be removed from the working relation. If there is a large set of different values for an attribute in the initial working relation and there exists a set of generalization operators on the attribute, then a generalization operator should be selected and applied to the attribute. Now let's understand this using an example. In given figure, we have two different tables. First table is the initial working relation, which has a collection of task-relevant data, whereas the second relation is the generalized relation, which is obtained after applying attribute-oriented induction. So let's understand how attribute-oriented induction works. This approach is applied for each and every attribute of the initial working relation. So starting with the attribute name. Name attribute has a large set of different values. However, we cannot generalize this attribute and that is why it is eliminated from the generalized relation set. Next is the gender attribute. Now, gender attribute has only two values, that is either male or female. So we do not need to generalize it. So we will keep this attribute as it is in the resulting set. Next attribute is major. Attribute measures value can be generalized to the higher level concepts which can has values like engineering, science, arts, etc. Next attribute is birthplace. We can generalize birthplace attribute with birth country. Next attribute is birth date. Now, birth date attribute has a large set of different values. So, we can replace birth date attribute with age or age range attribute. Next is residence. Again, the values of residence attribute has a very large set of different values. So that we can replace residence with residence city. Next attribute is phone number. Now, the phone number attribute contains a huge set of different value. However, we cannot perform generalization on this attribute, and that is why we will eliminate this attribute from the resulting set. And the last attribute is GPA. GPA has the large set of different value, so we can generalize it into the intervals, or else we can give the labels to the intervals like very good, excellent, average, and etc. So this is how we have performed attribute oriented induction on each of the attribute on the initial working relation and get the generalized relation as a result. Next topic is class comparison. Class comparison means descriptions that differentiate a target class from its contrasting class. If the target class and the contrasting classes share similar dimensions and attributes, then only they are comparable, otherwise not. For example, the three classes which are customer, product and location are not comparable because all these relations has different set of attributes. However, the product sales in the last 4 years are comparable classes. Also, the customer from town and customer from village are also comparable as both the relation has same set of attributes. The set of associated data from the databases and data warehouses is collected by query processing and is partitioned into the target class and contrasting class. The procedure of class comparison is as follows. It has 5 different stages. First is data collection. By query processing, we can collect data for both the target class and contrasting class. Second stage is dimension relevance analysis, in which only the highly relevant dimensions are included in the further analysis, though there are many dimensions. Third stage is synchronous generalization. It is performed on the target class as well as contrasting class, which gives a prime target class relation and a prime contrasting class relation. Dimension threshold should be considered while performing generalization. And then last step is presentation of the derived comparison. In this step, the presentation of the resulting class comparison description can be visualized in the form of tables, graphs and rules. The user can apply different OLAP operation to adjust the comparison description. Now let's understand class comparison using an example. So as you can see in this figure, we have 2 different tables which contains initial working relation of the target class, which contains the data of graduate students, whereas the another table is the initial working relation for the contrasting class, which has the data of undergraduate students. So first, we have to perform generalization on both the relation to get the most relevant data for the class comparison. So as you can see in this figure, we have generalized relation. First is the generalized relation for the target class, which has the graduate students data, whereas the next is the generalized relation for the contrasting class, which has the undergraduate students. Now we can perform comparison in both the tables in order to get some insight. This is how class comparison works. So that's it for this lecture. Thank you.